morning, everyone. We are starting a new section today, 5.3. So let's get this show on the road. Got all my little tweaks I have to do with the camera position. There we go. Right. So, section 5.3, we are going to be dealing with what is called the fundamental theorem of calculus, not just part 2, which we've met, but part 1 as well, and antiderivatives. So we're kind of doing the theory part of areas under curves and area functions and all that good stuff. And then pretty much after that's over with, and the rest of it, and there's a lot of questions in 5.3, are going to all be about finding antiderivatives, which we have met. But we're going to take that idea and we're going to kind of run with it as far as we can. So here's a guy that's new. It's called the area function. Notice this axis is called the t-axis. So you have a function y equals f of t, you know, like y equals t squared or something. And you have an arbitrary number, we'll call it a, could be 0, could be any number, right, a. And the area function is simply defined as the area of under the curve starting at a and finishing at some variable x, some value x. So can you see that g of x is actually going to be a function of x? Does that make sense? So it's kind of hard to do that exactly. So here's an example of it. This is question 1, where the function that's going to be called y equals f of t, I guess. This fella here, put it in red. Is made up of very straight lines. So if you're being asked to find the value of g of 0, right? Oh, and in this question, the a is 0, right? Because you're starting at 0. If you're going to do this guy, you're being asked to find the integral from 0 to 0 of this function f of t. Well, some kind of trivial. The answer is 0. Would you agree if you started at 0 and finished at 0, and the area between a number and the same number is always 0? So that one's a kind of starting point, but it's something. Let's do g of 1. G of 1 would be the area under the curve from 0 to 1. Right, 0 to 1. It's basically that bit, isn't it? So the area function would be 2. You see where I'm going with this thing? Right, what would g of 2 be? It'd be the area under the curve, always starting at 0, to start foiling in this case, to 2. Well, that would be all of this, right? The red bit and the green bit. You could do it different ways. I guess the easiest way is just to remember that that bit's 2 and then just add on the green bit, right? That would probably be the quickest. Can you trust me that that's 2 boxes? And that's 1 more, so the answer is 3. 2 add 3 gets you 5. And couldn't you keep going? And I will, for g of 3, g of 4, g of 5, g of 6, and so on. Let's do g of 3 then. So if you want to know the area under the curve from 0 to 3, just this bit here, it's that bit, and that bit. Now that's 2. Well, that bit and that bit are 5. And half of 4 is another 2, so I guess that's 7. Now things get sneaky. Really sneaky. Suppose I want to know g of 6. So I'm going to start here and get the area under the curve, starting here and finishing here. Just to remind you, won't this bit be negative? Won't the area count as a negative value? So what I'd probably do is find out what that guy is, which I know is 7. Find out what this bit is, and then it'll be a negative number. So that guy and that guy, when you put them together, we are done. So the integral from 0 to 6, the area under the curve from 0 to 6. Let's see what this guy is. That bit there is worth what, 2, and that bit there is also worth 2. So this is 4. but it's a -4. Can you see why that's going down to 3? Basically because of that, right? Now there's one last piece, this piece here. So the area curve from 0 to 7 of this function would be all of these bits and all of these bits and another -1. So that'd be down to 2. So what we've done here is create little snapshots of what the area function for y equals f of t is. Are we okay with what I just did there? Right. By the way, do you know this area function? The g of x that we're talking about? Start at any value you like, finish at x. This fella. Do you know what that guy is going to become? Any guesses? What do you think g of x is going to represent? Last chance. It's going to be the antiderivative of f of x. The g of x is going to be big capital F of x. So that's the first thing we want to do. So let me show you. You don't get a lot of shots at this, and I've kind of stole the show a little bit by doing one of them, but you know, it's too hard to create mine. Right. Can you see question 1 is basically the guy I just talked about. Now, it then goes on and asks you, when is it increasing? What's its maximum value? And what would its sketch look like? So one of these 4 pictures will be equivalent to that table. If you take the value G0, G1, 2, 3, 4, 6, and 7, if you plot little dots and then join them up with a curve, you'll be able to make it match with one of these 4 guys here. Right, so g of 0, g of 1, and so on. Why am I telling you right now that the area function g of x can't be that guy? Why do I know that's definitely not the right answer?
Because in that one, g of x is always decreasing.
Yeah, it's also negative, isn't it? Which isn't true for my table. And because it's not negative, I'm going to kill that one off. At least it's not negative at the start. So actually, it's not negative any of the times. So the only one of these shapes that's positive is this one. And you see it hits a maximum. In my case, didn't I have a maximum at 3? Because my g of 3 was 7, which is the biggest number. And that matches perfectly with that. That guy there is at 7. And that guy there has an x of 3. And then you have your own question, where you kind of do the same thing. So I'll let you go on with that when you need to. And that's the concept or the idea of what an area function is. So let me now show you the number 2 of the things we're going to do. The second concept. It's called the fundamental theorem of calculus part 1. We've seen part 2. We've used it last week, Friday. Part 1 isn't that helpful, doesn't get used much. So you're only going to see it for a little while and then it kind of disappears. So let's see what it says. The fundamental theorem of calculus part 1 states that if you find the area function, right, the guy we just did a minute ago, its derivative is the same as this function here, but in terms of x. Well, what does that look like? If I tell you that g of x is the integral from 1 to x of 1 over 1 plus t squared dt, right? So if I tell you this is my area function, the fundamental theorem of calculus says g dashed of x is the same thing as f of x, which in this case is 1 over 1 plus x squared. So that's basically f of x, isn't it? Only the x's are t's. So the derivative of an area function is this guy. what do you think the derivative of this area function is going to be? What's the derivative of this area function? Don't overthink it. It's actually quite simple. Oh, okay. This guy has a derivative of its area function as that guy. This guy last chance.
One over 1 plus x.
Yes. I'm wondering why people are pausing on that. You're thinking, oh, maybe you're thinking this 2 is important. Do you know the good news is that 2 or that 1 or that a or 0, this starting value has no effect on the answer, because won't that just give you a number, and won't derivatives of numbers disappear? So that guy says 2. If I made him 12, it'd still be the same answer. And this guy's 1. If I made him 100, it'd still be the same answer, right? So the number, sometimes they just write a, because it doesn't matter what it is, right? A just represents a constant. A to x is that guy. Okay, do another one. This one took a little bit more thought than I was expecting. Here's an area function. Pretend I didn't write that. I'll do it again. What is the derivative of the area function this time?
ln of 2 plus x squared.
Are you getting what I'm saying? It's not brain science here, isn't it? Simply just whatever that is with an x. And you're just accepting it because I'm not proving this. Proving it is ridiculously difficult. It's just a truism, right? It's true. It's called the fundamental theorem of calculus part 1. And it says the derivative of an area function is the same as that guy with an x. It's essentially what it says. Okay, just to make me feel better, I'll do one more. Suppose I have an area function. It's integral from, oh, I'll call it a this time, just to be even weirder, of x. And it's going to be the square root of 1 plus t squared times the sine of t over t plus 2 dt, right? So I went crazy. You're going to be asked what the derivative of the area function is. Would you all agree it's pretty straightforward what it's going to be? So the fundamental theorem of calculus essentially says that the derivative of an area function is the same as that function there, but with x's. Are we okay with that one now? Any questions? Because that's it done. That's, you've seen area functions and their derivatives. Okay, got nods. I feel good. Now, this guy you already know. Fundamental theorem of calculus part 2. These functions that we do all of this with, we're making the assumption that they're well behaved. Well behaved means they're continuous. There's no weird holes in them. There's no vertical asymptotes. You can differentiate them, right? They're just normal curves, nothing weird about it, right? So that's all I mean when I say well-behaved. If you want to find the integral, which is another word for the area, from a to b of any function, y equals f of x, we're back to x's and y's again, right? Nice variables that we're used to. If you want to find the area of this, it's just the capital F of b, take away the capital F of a, where capital F of x is the antiderivative of this guy. We spent a few, well, maybe an hours, but certainly 1 hour, I'm doing antiderivatives. Now, here's something I didn't mention, but it's also true. Isn't the derivative of the antiderivative just the original function? So if you take a function f of x and you find its antiderivative called capital F of x, if you now differentiate that capital X, don't you get back to f of x? Isn't that why it's called an antiderivative? Take any function you can think of, find its antiderivative, and then differentiate it. I bet you get back to the same function you started with. So you can think of, if it helps, that capital F of x is just the same thing as the area function, which is kind of right back to the beginning of the section, right? You know the g of x area function? G of x is also the antiderivative function. Any questions about that guy? Are we good? Right. So from now on, for the rest of today, and I'm pretty sure tomorrow as well, we are going to get really good at finding antiderivatives. Because what that's going to allow us to do is find areas under curves. And there are two versions of the same question. Here is the first version. You might be asked to find the area, right, the integral from 1 to 2 of x squared plus 4x minus 1. So let's just remind you how that works. Don't you find the antiderivative of this guy? So add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. And what's the antiderivative of minus, whoops, make it plus now. What's the antiderivative of plus 1?
X.
Yeah. And then we are meant to, according to the fundamental theorem of calculus part 2, aren't we meant to evaluate the antiderivative at 2, take away the value of the antiderivative of 1? And the way that that working is typically written, almost universally, is you put a big vertical line. It's just a way of setting out your working. And you put an x equals 1 and x equals 2. So when a French guy looks at this, he's going to say, oh yeah, you're going to take this guy, I can't do French, right? And you do 1, you're going to plug in 2, and that is what we do next. So 1/3 times 2 cubed plus 2 lots of 2 squared plus 2, take away 1/3 of 1 cubed plus 2 lots of 1 squared plus 1. And that's 8/3. That's 8, and that's 2. And that's 1/3, and that's 2, and that's add 1. I'm making a meal of this, but anyway, 8/3 add 10. Take away 1/3, take away 3. So what does that get me? It gets me 7 and 7/3. 7 is 21, so eventually I get 29/3, I hope. Are we comfortable, provided I managed to do that in my head correctly? Are you comfortable about the mechanics now of getting an area under a curve? Find the antiderivative, plug in the top number, plug in the bottom number, subtract the two answers, and then make it look pretty. In this case, that looks pretty. So now I'm going to check if I've done this right. Now you don't need to worry about checking on WebAssign. Won't WebAssign have a big green tick that says you did it right, and a ugly red cross if you screw up? So I'm going to go y equals, I'm going to take this function in. So that's x squared plus 4x, add 1. I'm going to go to the window. I'm going to say from 1 to 2. I'm then going to do zoom 0, which is zoom to fit. And pretty boring. Looks like it's a straight line, but technically it's a curve. And then I'm going to go second calc and option 7. And I'm going to say start at 1. Upper bound 2. And I better see 29 thirds, at least 29 thirds as a decimal should be 9 point lots of 3s. Let's find out. Okay, what does that tell me? Tells me I'm wrong, doesn't it? The correct answer should be, do I have to put it in again? Yeah. Okay. 1, 2. The correct answer should be that fella. And I got that guy. So let's see what I did wrong. 2, 4, 8, 8 thirds is good. 2, 4, 8 is good. 2 is good. 1 third, 2, and 1 is good. 8 thirds add 10. Take away a third, take away a 10. Okay, I'm going to do that in the calculator. 8 thirds, add 10, take away 1 third, take away 3. There's the guy. Make that a fraction. There we go. I didn't count right. But did you see how using the calculator I caught it? Now, all WebAssign will do, as all the calculator will do, is WebAssign only tells you it's wrong. Doesn't the calculator tell you what it should be? So at least you can have a quick look and say, oh yeah, I screwed up with my fractions. I'm one too many. It should have been 28, not 29. And don't just do it. I mean, you know, oh, I'll write the answer down because I know it's right. Make sure you find out why you did it wrong. There, I just couldn't count. That's all I did wrong. And the calculations were fine. Pretty powerful technique. Now, I said there's 2 versions of this question. Here's the second one. And in this case, you find the antiderivatives. And you just put a big plus c at the end. When there are no limits of integration, this is an indefinite integral. When there are start and finish numbers, it's called a definite integral. They're pretty good names, would you agree? Indefinite, you're not 100% sure what's going on. Definite, you're certain. I'm certain that's the answer, right? Why am I indefinite? There's a plus c here, right? There's a little bit of unknown going on. Not as cool. Are we good? Right. I'm going to focus what's left of today on indefinite integrals, because isn't this just a matter of plug and chug? Right. So if you can do one of these, can't you do one of them? Right? If you know how to do this, the only difference when you do one of these is doesn't that disappear and you just put in numbers. So what is the antiderivative of 5e to the x? What function would you need that if you differentiated it, you'd get 5e to the x as your answer?
Wouldn't it still be 5e to the x?
Yes. It's one of my favorite functions because it's the one I screw up the least, right? What about 3 times the sine of x plus a cosine of x? Antiderivative of 3 sine x and then the antiderivative of plus cosine x and stick them together with a plus c at the end. Right, let's do the sines then. Antiderivative of 3 sine x. Be careful about the sign.
3 negative cosine x.
Yeah, we'll stick the negative at the front. What about the antiderivative of a cosine x on its own like this?
That would just be plus sine x, right?
Yeah, and then you just stick a c.
And then yeah, plus c.
Right. How about the antiderivative of that guy? Well, I'm going to call him that guy. And the reason the reason for doing that is there's a lovely rule called the power rule, which says if you want to find the antiderivative, right, of any guy that's written as a power of x, regardless of what that n there is, don't you just add 1 to the power and divide by the new power? So if you call a square root a half power, it makes this adding 1 to the power a lot easier. Add 1 to the power. You get 3 halves. Oh, yeah. That's not there anymore. Add 1 to the power, you get 3 halves. Dividing by 3 halves is the same as multiplying by 2/3. That's where that came from. Now, if I have done this correctly, shouldn't I be able to differentiate this and get back to that? We're all good at differentiation, right? Differentiate that, you do get back there. But that's not considered good form. Remember style points. Make
Yeah.
your answer look like the original. Now, if someone gave you a question and it looked like that, right? That's the question, right? They gave you it like that. Your answer is that. But when you give me it as a square root, I mean, it may be nitpicky, but it's important. You see, one of the major rules, at least, that we're going to be concerned about is style points. Make it look pretty, right? Make it look like the original. That's probably going to be the biggest rule of them all. And then there's some obvious rules. You're never going to write 4/8, aren't you? Always going to call it a half, right? Things like that are so obvious you wouldn't even think of it as a rule, I hope. There is a third rule that is kind of forgiven if you don't do it. And that's, if it's possible, you should try and factor things and make them look pretty. How about this fella? Is there a better way to write that expression so that we can do it?
10
Wait.
times x to the, is it -2?
It is.
Oh, yeah.
Now, all I'm doing here is rewriting it in a way that's going to let the power rule be usable, right? Right now, you can't really do the power rule in that. If you tried, you'd 50% chance that you screw it up, right? But you write it this way, it's easier. Now, the rule is add 1 to the power and then divide by the new power. Are you happy about that? Add 1 to -2 gets you -1, and then divide by -1 gets you that guy. But remember style points. And now we're finished. How about this one? Can I use the power rule on this one exactly as it is? I don't need to change it. Can I use the power rule on this one?
Yeah, I think so.
Now, add 1 to the power. Well, if you add 1 to that guy, don't you get plus a quarter?
Yeah.
Now, dividing by a quarter is actually the same thing as multiplying by 4. Style points, is that good? Yeah, because wasn't the original a fraction, so it's okay for the answer to be a fraction power. This guy needed to be turned into this one. This guy didn't need to be changed. So, you know, it depends on what you start with, what you're going to end up with. How about this question? Hey, wait a minute, you've changed the letter on me. Where's the X's gone? There's Y's there. Well, in mathematics, those 3 are for all intents and purposes essentially the same thing. Would you agree that the variable is a placeholder for a relationship? You could use any letter you like, but we tend to keep to the end of the alphabet. So whatever the answer to this is, will be in terms of Y. Whatever the answer of this is, it's going to be in terms of X. And whatever the answer to this is going to be in terms of T. But won't the answers be algebraically the same expressions, just with different variable letters being used? So don't let the letter of the alphabet that they decide to use be a hindrance. Treat it like it was an X. It works. Now, this guy is good, and this guy, not so good. This guy, I'm going to replace by this fella. Why am I doing that?
So you can use the power rule.
Right. So when I add 1 to power, I get -2. When I divide by the new power, this becomes -2. When I add 1 to the power, and then I divide by the power, and then I add my C, and then I have a quick look. And my quick look is style points. Any of those guys need to be changed.
The first one.
And when I change it, we're good. Secondly, if there was numbers like 1 to 2 on this, would you agree it's much easier to get answers, because they're going to be fractions probably, when it looks like this, when there's numbers? If I said to you, I don't know, -2 to the power of -2, you may have a problem trying to figure out what the heck that's equal to. Would you agree? But it's a lot easier to say -2 over -2 squared, and you can get the answer pretty straightforwardly. So even for calculation purposes, style points is going to be helpful. Is there any questions that I've done that you would like me to talk about, or are we good so far?
I did have one,
Go
but
for it.
I went over it last night and I just wasn't, it was the converting an integral to sigma notation, and I just didn't distribute delta x. I just slapped it on the end. That was the only thing I was doing wrong. I was so stumped.
Oh,
It just turns
is
out I
it?
wasn't distributing.
So you fixed it yourself then?
Yeah, I just thought it was funny.
Oh, hey, I've done stupider things than that, so don't feel bad about it. I've done some really bad things. Okay, let's try some sneaky ones. Sneaky and deliberate to try and catch you. Antiderivative of that guy.
The square root of 2x
correct?
plus c.
If someone had said, I want the integral from 1 to 2, then all you would do is make that go away. And you do x equals 1 to 2. And you'd have square root of 2 times 2, which is that guy. Take away the square root of 2 times 1, which is that guy. And won't the answer simply just be the square root of 2? Here's another one to catch you.
It's still E, isn't it?
No, because it's not to the
Yes.
power of x. It would just
Yeah.
be x, wouldn't it?
Yeah,
C.
plus the c. You see that,
Plus the c.
sneaky? Right? Now, if I said to you e to the x, which is not the same thing as e, I guess if you want it, you could call it e1, but it's not the same thing. Do you notice that there's a big difference between that guy and that guy? Even although they're not that much difference when you look at them superficially, right? There is a big difference between what that means and what that means is. One of the common mistakes that people tend to do with antiderivatives is that when the thing is a constant, meaning a number like e or square root of 2, they sometimes try and use, say, the power rule in it or some other rule. That's not necessary, right? So watch out for that little trick. Oh, let's put some numbers on this one. Suppose I asked you to find this fella. Right, so we're doing a definite integral. Well, we already have decided, right, that's the correct answer. It's going to be evaluated at -9 and at 9. Right, if you plug in 9, you get e times 9. Take away e times -9, which ends up being 18e, right? 9e plus 9e is 18e. And that's it. Don't turn any of these guys into decimals. 18e is the correct answer. Done two things to this question to make your life a little bit harder. First one, I think you'll be happy with. Isn't it okay the u's don't make a big difference? Right, it could have been x plus 1, x minus 2 dx. But the second one is, oh, what in the heck are you going to do with that?
I'm just gonna foil it.
Yeah. To save time and money, will you agree with me that's what it eventually becomes? Now I can do the power rule. Slap a C at the end and call it good. Let's try, oops. I'm gonna just mute you all, so you're gonna have to hit spacebar now. Now, how about this puzzle? The integral of 2 take away t times the square root of t dt. Give you a few moments to think this one out. Any suggestions what I should do next?
Multiply the square root of t in.
Multiply the square root of t. Is that what you said?
Into the 2 minus t, distribute it.
Okay, so that's going to be 2 square root of t's. Okay, what do you get if you multiply t and the square root of t together?
3 halves.
Oh, good, yeah. So t square root of t, so little side issue, isn't that t times t to the half? We don't call it 1.5, we call it 3 halves. You happy about where these 3 halves came from if you're saying I wonder what you did there? Right. We've got a problem, don't we? Just a little one. Once we fix it, we'll be good. What's my problem? What's our problem?
The remaining square root.
Okay, what are we going to do about it then?
It'd be power of 1/2.
Do you see that those 2 lines were just to get it into a form that allows us to do the power rule? I mean, the power rule is very versatile. Not the prettiest powers of t, but they are the ones we're going to use. So I'm going to add 1 to the power. Right, so you add 1 to that, you get 3 halves. Divide by the new power is the same as multiplying by 2/3. So that's why that's now 4/3, right? 2 times 2/3. Now, take away. Add 1 to this guy and you get 5 halves. Dividing by 5 halves is the same as multiplying by 5/2. And then style points. 3 halves is the square root of t cubed. And 5 halves is the square root of t to the 5. Are we good on that one now? Make sense? Last few things. While I'm doing this, you probably should say hi if you haven't already. Every time I've been doing style points, especially these fraction ones that turn into, say, square roots and cube roots, that kind of thing, WebAssign, unfortunately, will probably accept this answer. I wish it didn't. I wish it forced you to do that answer. Because this is the correct answer. You know, okay, that's not wrong, but it's like 95% right, but it's still not 100% right, okay? So we want to be 100% right. We want to be consistent in the way we write our answers. That's another feature of style points. The way I do it, and the way a Frenchman should do it, and the way a Chinese person would do it, or whatever kind of person in the world we're talking about here, we all kind of came together and said, let's all do the same thing. Isn't that why you'll never see in a good textbook, or any textbook, 1x? Haven't we all decided that style points, that's called x? You'll never see 0x. Everybody has decided that 0x is just 0 anyway. In fact, wouldn't you very often never see 0 unless that's the only answer that's left? If it was 0 plus t, you just say the t. Okay. So style points, important to get the right answer. Can't push it enough.